Now at this stage, we've done an awful lot when it comes to calculating what you might call a general antiderivative, or indefinite integral as we refer to them. The trick is, in applications, you don't always want a general antiderivative. Instead of that family of functions kind of scaled by this arbitrary constant c, you want one specific function doing one specific thing. In that instance, you're technically solving what we might call an initial value problem. But at this point, you really have to ask whoever's demanding the specific function, yeah, I need some more data. So, sorry for the shaking thing there. I moved something. My bad. So, coming back to take a look at an example of one of these initial value problems, let's consider. So, we want to find a function f of x. And we know what we want its derivative to look like. So for some reason or another, we want this weird derivative where we've got a power function, and then an exponential sitting along with it, and then a trig function at the end. So for some reason, we need this. Now, we also need a specific extra piece of information. So this is where the initial value part of this comes in. So I need this thing to have a value of 13 when x is equal to 0. So we're more or less specifying now which of all of the possible antiderivatives we want by saying we want the one that goes through this specific spot. Okay. As it turns out, we've already got most of the tools we need for this. We just kind of need to make one extra step. So first, we know that an antiderivative of this thing, so going back from f prime to f, we can follow the same procedure we've been doing. It's going to look like what we do if we follow our antiderivative rules, and then we have the plus c sitting on the end. So work this guy in right here. So we got that, and we're going to find antiderivatives using the rules on our best friend sheet. So we can use the power rule here. Exponent goes up by 1, divide by that new exponent. So we have 5/7 x to the 7th. The exponential function, he's my favorite because I don't have to work real hard on him. His antiderivative is just, e to the x again, so minus 3e to the x. The cosine function, the antiderivative there is sine of x. No negative in this instance. So, now, am I done? Of course I'm not done. I haven't written my constant of integration on here. So I've got plus c floating around in that spot. The trick is, we're going to have to pin down exactly what value we want for c. And to do that, we use this guy right here. The initial data are going to give us what we need to work through this. Well, we know that when x is 0, we want a value of 13. I can plug x equals 0 into this monster. And you can work through the arithmetic here. 5/7 times nothing, it goes away. The sine of 0 also vanishes in a puff of logic. 3e to the 0, he doesn't go away, because e to the 0 would be 1. So negative 3 times 1. So we have negative 3 plus c. Now we can get c by itself, algebra 1 style. We add the 3 over here. So our c value is 16. And it's usually good form to fill that into what you're working on. So we have 5/7 x to the 7th minus 3e to the x plus sine of x plus 16. And we have satisfied our boss's concerns. So we've got a function. Its derivative, you can check, will drop back to give us this. And if we plug x equals 0 into this thing, we just confirmed we're going to get 13 out of it. Awesome. Now, this is an example of, it's a really, intro kind of thing to what you might call solving a differential equation, an equation involving a derivative that we saw right here. That's one of my favorite subjects. I'm intentionally cutting myself off now so the rest of this video doesn't turn into me telling you how awesome differential equations is. But really, if you get a chance, take this class. All right. So I've got one more example I want to take a look at, and then I will set you loose on some unsuspecting homework problems. This one is going to be a bit more applied in nature, and it's actually going to require us to repeat this process twice because we're actually going to start with a second derivative. So we actually need to find two antiderivatives to get back to an initial function. So the context of the problem is we got a guy. Let's call him Jimmy. So Jimmy, he's having a rough night sleeping. He's tossing, he's turning. It's really bad. He's having a bad dream or something. Eventually, he tosses so hard he throws himself off the bed, and now he is a projectile headed toward the floor, toward Jimmy. So Jimmy is starting from 3 feet off the floor. A yard up seems not unreasonable for the height of a bed. So Jimmy's roommate is apparently kind of a jerk because instead of trying to help Jimmy, Jimmy's roommate pulls out a radar gun and clocks him so we know how fast he's going. Jimmy's roommate may need some counseling. So Jimmy's initial velocity is -1 feet per second. So he's going downward. That's why it's negative. So now, we want to come up with a position function describing where Jimmy is relative to the floor at a given point in time. So we're going to have to work backwards using the same kinds of moves where we would start from position and then make our way towards acceleration back in Chapter 2 when we first introduced derivatives. So we can start from acceleration, ignoring air resistance like we're prone to do in Calculus 1. Jimmy is an object in what we call free fall at this point, and his acceleration we're assuming is constant. So yeah, there's some stuff going into the assumptions there. It's okay, just roll with it. So acceleration is -32 feet per second squared. As always, I apologize heartily to those of you who prefer metric units. This is what we're going with. So -32 feet per second squared. So we know that acceleration is the derivative of velocity. So if we're given an acceleration, to get a velocity, we're going to have to take an antiderivative. So I didn't really need the parentheses there, but I wrote them, so we're going to go with it. So v of t is -32 dt. This is a constant. So what function would give us a derivative of -32? -32t. But not done yet, right? What am I missing? Exactly, I'm missing the constant of integration. So I need to put that guy in there. Now, our initial velocity, that's what v of t should be at t equals 0 when Jimmy's jerk roommate, clocks him and starts paying attention. So v of 0 is -1. We feed that in here. 0 going in for t. I'll be a little pedantic. I wouldn't have held it against you if you hadn't written this because 32 times 0 is 0 and then it vanishes. If you had just said -1 equals c, I get it. So v of t is going to look like -32t minus 1. Units are feet per second here if you're needing to track velocity at this stage, but we're really after position. So we need another antiderivative. We've got to come up with another indefinite integral, and then we're going to need to pin down another constant. So now we can use our power rule. Exponents 1, adding 1 to that gives us 2. Dividing by 2 would leave me with -16t squared, an antiderivative of that -1. It's t, not x. Don't put an x. And I'm going to call it C2. If you really just labeled it C, it's not the end of the world, but I want to make sure you know that this is not automatically the same as that guy. So now we know that when t is equal to 0, Jimmy was 3 feet off the floor. So 0, this goes poof, 0, this goes poof. All that we're left with on the right-hand side is C2. So our position function is negative 16t squared minus t plus 3. So that is that. The actual question I really want to pose at this point, and how I originally came up with this problem to begin with, is trying to figure out exactly how long it takes poor Jimmy to hit the ground and realize, he's just smacked his nose into the floor. So that's a problem for you in your upcoming assignment. So that's covering everything I wanted to talk about as far as antiderivatives are concerned. So next time, we're going to talk about something completely different. At least it looks that way. So take care.